would like, if I may, to take you on a strange journey of reference objects, value objects, iterable, strange new loop, sets, and hashing. We'll start with a class to represent a phone number. It's a pretty stupid class, we'll see later on. At the moment it more or less just looks like a struct, which contains a single value, which is member, a number, the phone number. Let's write our test code. Don't worry about some of that stuff, I'll see that in a second, but here you see the main function creates a new phone number called A, a phone number called B, a phone number called C, assigns to the attributes the actual phone numbers. They're not very good phone numbers, are they? 0, 0. Well, that's a bit confusing, isn't it? I can't start the phone number with 0, 0 like I'd like to. Why ever not, I wonder? It's a little puzzle. Do you know if you start a number, thanks C, with a 0, the compiler assumes you're talking about an octal number. So that would be a nasty surprise, wouldn't it? We want decimal numbers here. So that's the number 0099. Okay, so it's not a very good class to represent phone numbers. Now, first of all, I want to show you a set. If you want to have a collection of stuff, up until now we've basically been using arrays or implementing linked lists ourselves by having objects containing other instances, other objects of the same class. But if you want to just have a set of stuff, which means a collection of things in no particular order but no duplicates, then Java has a built-in class which lets you represent a set, which is nice. It's parameterized by the name of the object contained inside the set. So this is a set of phones, which is very convenient. That's Java generics being able to be polymorphic in this way, to parameterize it over another type. We're not going to talk much about that, but we will gleefully use it, this facility of doing this, but we're not going to write much ourselves. So we've got known numbers, which is a set of phone numbers. That rhymes unintentionally. And let's initialize it. Well, we have to create our empty set. Now, set, it turns out, is, let's just have a look over here. As you can see, set is an interface. It implements two other interfaces itself. So in other words, anything that implements set also implements these interface collection, which is the general Java way of storing lumps of stuff. So the collection interface is a really important one. And iterable. And if we look at the iterable interface, set is iterable. And what does it mean to be iterable? It means you've got a single function called iterator that returns something of type iterator, and we'll look at that later on. Okay, but basically I just wanted to show you what a set was. A set has all the normal operations you'd expect on a set. You can add something to the set, add lots of stuff to the set, clear the set, check if the set contains something, check if another object is equal, another set is equal to this set, another object is equal to this set. Return the hash code, talk about that later, check if the set's empty, so on and so on and so on and so on. Okay, all right, let's return. So we've got our set here. Oh yeah, but because set was an interface, we can't say new, make a new set by going new set, because you can't make an instance of an interface, you've got to make an instance of a class. So we need some classes that implement that interface. If we go back to the Docker where we're just looking, classes, okay, here are the classes that the Docker knows about which implement the set interface. So if you wanted a set, you could have an enum set, a hash set, a linked hash set, or a tree set. I guess here we're seeing why interfaces are quite neat, and in fact support ADTs in a much nicer way than C does, the way we did in C at least. You can have the concept interface, the abstract sort of API, all things that a set should have. All sets should have an add, subtract, check if the set's empty, check if an element's in the set, so on, so on, and so on. But there's lots of ways of implementing it. In C, the way we separated the .h file from the .c file meant we could swap implementations, but we had to do that at compile time. Notice the nice thing about Java here is you could have an enum set and a hash set both existing at runtime, and just use either of them as a set. So it lets us have multiple ways of implementing a set, and also lets us have them all there in front of us at runtime and mix them and match them and so on and so on and so on. Now the way we're going to implement a set is a hash set, and that simply stores the elements and detects if they're equal using a hash table. Stores them in a hash table, detects if they're equal using a hash table. It does all the stuff, the mechanics of maintaining the hash table in the background. We don't have to worry about that. It uses the function that every object has. You might remember every object inherits from the class object, and we had a quick peep at the functions that, the methods that all objects have, and one of them is a hash value. So every object has a hash value. That this is quite convenient when we implement a hash table, or when Java does, or when this library does, because it'll just use that hash value to hash into the table. Okay, so we've got hash set is a legitimate way, it's a class, it's a legitimate way of implementing a set, and you'll see it just has all the sort of set functions: add, clear, clone, contains, is empty, iterator, remove, and size. Okay, so back here we're going to say our set is a new hash set. It's a set of phone numbers. Create it please, that's a constructor, and it will initially be empty, and we have to import the appropriate classes, so Java knows what the heck we're talking about when we say the word set. It now knows when I see the word set, I think Richard's talking about java.util.set, and when I see the class hash set, I think he's talking about java.util.hashset. Okay, so now we're going to add the numbers to our set, and then we're going to print them all out. This is our test code. It's not very interesting, is it? I guess what we're doing here is we're creating a couple of phone numbers, putting them into a set, and then printing out the set just to show you that we have a set of phone numbers. How do we print them out? Well, this is a slightly interesting thing. Because this is main's a static function, and it's calling this function without us creating any objects to actually call it on. This is itself also a static function, of course, the print phone list. It's given the set of phones, and we want to print them all out. Now, we could do this in a couple of ways. We could, I guess, if we were really keen to implement it ourselves, we could duplicate the set and then pick an element out of the set and then delete it from this, print it and then delete it from that set and iterate until the set's empty. Though how we'd find an element in the set might be quite hard. What we really want is to have a function that gives us a list or some sort of sequence of all the elements in the set. And those of you that know about recursive and recursively enumerable sets will find this thought quite interesting. So Java does that. Do you remember the set function, the set interface? Let's go back and have a peep at it. Has a function called iterator, and that returns an iterator over that set. And indeed, because it has the function iterator, it's allowed to be in the class iterable, because everything in the class iterable just has to have a function called iterator. So sets are iterable, and that means we know we have an iterator function for them. And the iterator function, if you look at it, where do we do it? Here. So we passed in our set of phone numbers, and we're going to, on those phone numbers, call the iterator function, which will return an iterator, which we're going to call all. So all is an iterator over the phones, over the phones in the set. So it's an iterator of phones. So this type has to match that side. Yeah, you got a set of phones. You can produce an iterator over them, something that can step over them. That's what all an iterator is, something that steps over them one at a time, handing each up to you for your inspection. Oh, here's the next one, Richard. Oh, here's the next one, Richard. Oh, here's the next one, Richard. Every time you ask it, and what it's showing you is phones, because it's given a set of phones. So this creates an iterator called all. And now, here's the convenient thing to do. I can just say, while the iterator has a next, has something else to show me, then phone current, so we'll make a local variable called current, that's equal to all.next. So that is, all is the iterator, that gives me them all. Next is the next phone in the iteration. So this is saying, inside the loop, it's a fancy way of saying, one at a time, step through all the phones in the set of phones and as you get each one, assign it to the variable current here inside the loop, and then we'll just print out the number of current. All right, let's run that code. You can see that the four numbers were printed, and they weren't actually in the order that we entered them into the set, and they weren't in reverse order either, were they? That's a bit odd. I wonder why it picked that order. I guess that's the order probably of the hash functions, of the hashes of those objects. It probably did it in ascending hash order, I guess. I've got no idea. But that's a set. A set has no intrinsic order, so you put things in a set, you print the set out, the actual order is lost. If you needed to keep the order, it wouldn't be a set, would it? It would be a list. By the way, let's just see, just for fun, if I'm interested in why it picked that particular order to print them out. Let's also print out, just for sort of diagnostic purposes, what the hash value of each of the objects, each of the phone objects is. And that will that might show us that they're in increasing order. There's hash plus next line. Has hash. What are we calling the phone? Current dot hash code. Because it's an object, yeah, so it's got the hash code function. Print them all out. Let's have a look. Oh, I love experimenting. Oh, what's happened here? Mistake. And it's saying unresolved compilation problem. Got too many closed brackets. Oh yeah, I do. Oops. You should have told me. Why didn't you tell me that? If I was in the lecture at this time, you'd be telling me, wouldn't you? Here we go. That has hash. Oh, this is looking good. I wish I could space them out a little bit. Why don't we? All right, well, let's just see if they look like they're in increasing order. No, they don't, do they? No. They're in crazy order. Oh, well, so much for that theory. Okay, let's return it back to its beautiful, pristine state. Check it still works. Okay, so you've now seen what a set is and how to iterate over a set, but actually the whole reason I'm showing you these phones is I'd just like to talk about oh, and by the way, when we generated, we needed to use the iterator class. Yeah, we made an iterator, and that's also in Java.util. So the reason I wanted to show you this was, well, actually, rather than me saying that, sorry about being cryptic, let's write another function that uses the iterator. And in fact, I have one below. Smallest. This function here, whoops, stop that. This function here is it returns a string containing the number of the smallest phone number. That's the numerically smallest. So if your number was 555 1234 and someone else's phone number was 555 1999, then the 1234 number would come first, would be the smallest of those two. So what we want to do is step through the whole set, finding the smallest number and return a string representing it. Okay, it's a completely arbitrary function. It's crazy, isn't it? I can't justify it. I just wanted it. It's solely here for demonstration purposes. So first of all, let's check that we haven't got an empty set of phones, because there is no smallest of an empty set of phones. Should probably also check. Crazy. Okay, let's see. So we've got our phones. I've got some phones in the list, well, not in the list, in the set. So let's create an iterator over the set. Let's arbitrarily start with the smallest. And what we're going to do is we're going to step through updating smallest as we see. We're going to have some sort of flag we carry, not a flag, just the smallest so far, I guess. Oh, that's probably a better name for it, isn't it? Smallest so far. Let's refactor you. So initially the smallest so far is just an arbitrary one. The first one, oops, what happened there? set the first guy to be the smallest so far, then just step through the list, and if the current one we're looking at any given instant is smaller than it, then update the smallest so far, otherwise just leave it untouched, and at the end print out the number of the smallest so far. So that looks alright. And why have we got a warning here? It's never used. Oh, that's right, it's not used, is it? Let's use it. System count smallest number is plus smallest. Call the smallest function on our set of numbers. What's our set called? Called known numbers. Alright, there we go. Let's run it. Ba-ba-bum. Okay, so everything looks okay. We've printed out all the numbers as we did before. We found the smallest number and that worked. Okay. Now, this iterator is quite convenient. The annoying thing, or one thing I find annoying at least, is that arrays themselves are not iterable. Now, it'd be nice to be able to iterate over an array, wouldn't it? Because you do that all the time. But unfortunately, you can't create, arrays don't have an iterator function. You can convert them to something else and then get an iterator out of that. But for just directly iterating over them, it is a slight pain. There's another way of doing loops, though. That's what I'm leading up to. Dun, da, da. Java 5 and onwards introduced a new way, a for each loop, which lots of other languages have. It's just a bit of syntactic sugar, but it's very nice syntactic sugar, and it makes loops very simple. And we like simple, because simple is less likely to have errors. So I've actually made one before. Here we are, let me copy it up and you can gaze at it in all its glory. Phone list 2, I called it. Alright, we've got the phones, and we just say for every phone called current in all the phones, do this loop. So it anything that's iterable, that implements the iterable interface, and for arrays as well, Java will interpret this syntax to generate an iterator behind the scenes and step through for us. So this is very convenient. Just look at it, isn't it beautiful? For pick, take your collection and call what you want the current instance of the collection to be, give the right type for it, which has to match here. We've got a set of phones, so this is a phone. And then everything inside the loop now can refer to current, and it's talking about the current element in the iteration. So that's very, very nice. Let's print that out too. Go. And it's printed out the list, the first printout, and it prints out the smallest number, and then we iterate over the list and print out, oh dear, what's happened there? Oh dear, doesn't seem to have printed out the list right. Oh, well, you might want to think about that. What on earth has happened? You think about that. Well, I'll just take a quick break. Okay, did you get it? Can you see what happened? It's not actually a problem in the printing out, it's a problem in the smallest function. You look at the smallest function, our problem is here. And here. We're mixing up value and reference semantics here. This would look fine if we had, this would be absolutely fine if we had some sort of primitive type where everything's done by value. But we're fooling around with phones which are objects, and so they're done by reference. So when we say phone smallest so far equals all.next, give us the first guy in the list. Next at the beginning is the first one. We're not creating a local copy of the first element. Smallest so far now is a reference to that first element. We've only got one first element, and now smallest so far also points to it. So down here when we change, stop that. Down here when we change smallest so far, we update it with the current one, we're actually updating the first element in the list. Yeah. So the first element here, we're changing it. This is an aliasing problem. Because we're dealing with a reference to an object, you can have lots of other objects, object references pointing to that object too, and you could think that you have a local copy of it, but you've got the original one. So it's sort of like, well, what's it like? It's like if I had something and I wanted to show it to everyone, instead of giving everyone a copy for them to take home, if I somehow gave them a link to the original, then I'm really being trusting of the whole world, aren't I? That no one that I give this link to the original to will actually go and change and bugger up the original. It's like if somehow you went to the Louvre and you got a postcard of the Mona Lisa, but it wasn't a copy of the Mona Lisa. What it was really, through some sort of space-time continuum warp, a reference to the Mona Lisa, but shown a bit smaller. So it was literally the Mona Lisa itself. And you start to give everyone in the world postcards of the Mona Lisa. You're really trusting that no one's going to give that postcard to a kid who's going to scribble on it, because that would scribble on the original Mona Lisa. So we've got this problem that sometimes, when we talk about things, when we talk about data, we can be thinking of it as data, literally the data itself. And so, for example, the number 5, you could have 17 variables each containing the number 5. They're not containing the same number 5, are they? They're each containing their own number 5. And when Java compares them, or when we compare them in a program with greater than or equals or whatever, we're comparing them by value. We're not saying, are they the same number 5 stored in the same memory location? We're saying, do these two memory locations store the same value? But also in Java at the same time, we've got references, which are pointers to objects. And when we've got reference semantics going on, then when we compare things, we literally, if we use double equals, we're saying, are these the same thing? Not do their fields have the same values, but are we talking about the same memory location? And when we change it, we're not changing a copy of it, we're changing the original thing. Okay, now if you're just thinking one way or just thinking the other, and you were really strict with yourself, everything would be fine. But the problem is sometimes it's really convenient to think about things as data, and sometimes it's really convenient to think about things as objects. So let's look at our phone number. I picked that example because it's used in the refactoring book as an example, but also I picked it because I kept thinking of other classes myself that I could use instead of phone to represent phone numbers, and I couldn't find one that was as good, because the property I wanted it to have was it was plausible to think of a phone as a phone number as a piece of data, and it was also plausible to think of it as a reference. So let's look at our phones. In our program, the decision we have to ask ourselves when we're designing the phone class is, in our program, do we want objects of type phone to be reference objects or data objects? Do we want people to be able to make 100 of them, 100 different ones, give each of those 100 the same phone number, and have Java regard those as all being the same, even though they're stored in different locations? If so, it's a data object. Or do we want it to be a reference object? Do we want to hand it to people and know that we're giving everyone a pointer to a reference to some primitive underlying, not primitive, but underlying memory location? I'm not saying it very well, but do we want everyone to be referring to the same thing? So when they compare them, they're literally comparing to see if the things are the same. If so, then we want it to be a reference object. Now you could sort of plausibly think of phone numbers as data objects or reference objects, which is why they're quite nice. Let's pick some other classes just to make that, so you can see what I'm talking about here. If we were representing a student, that was one of the classes I toyed with. Is a student a data object or a reference object? Let's think about that. Well, a student would, I guess, store the name of the student and the student's number, and maybe it would store their address. Okay, do we want that to be a data object or a reference object? I reckon if it stored all the information I've told you about just then, you'd probably want it to be a reference object, wouldn't you? Because you'd want to have it so that various elements of the program might hold, a particular, might have been passed a student for various purposes. You'd want to have it so that if the student changed their address, presumably you'd want all those parts of the program that were containing references to that student to also change their address, to have the updated address. In other words, with a student, probably what you'd want then is to have a single canonical piece of memory somewhere storing the data on that student, and to make sure that everyone had a pointer to that, a reference to that object, that piece of memory. And if anyone tried to make a new student that was that student, tried to get a new instance of that student, they'd somehow be given a reference to the original one, rather than having, what you don't want to have in this case is, I hope you can see, two different objects stored in different memory locations, each containing the same data about that student. And I hope you can see that would be a problem then if you're using reference semantics, because at any given instant, various parts of the program having a reference to that student might have a reference to one or other, but not both of those objects. And so one object being updated or changed would change some of the references to that student over the program and not others. That'd be a mess. So basically, the approach is you should either go for reference or for data semantics for objects like this, where we're storing our data. If it's data semantics, then we want to make sure that that when people compare them, they're not comparing them for reference equality. That if I make 17 phone numbers each containing number 99, I'd like them all to be equal to each other, even if they're stored in different memory locations. And I also don't want anyone to be able to update any of my data objects, do I? Because then I've got this problem that that update will propagate through some but not all of the data objects, depending on who's referring to which object. And we'd like that to be transparent to the user. It doesn't matter which one you're referring to. So this is a long-winded, roundabout way of saying, if you're going for data semantics, you want to make sure that your data fields are immutable. You don't want them to be changed, because if they're going to get changed, then we've got this update problem. And did I put the word final on the wrong spot? Final. This is my final offer. There we go. And what's happening here? Why? Hey, we've got a grumble. What are you grumbling about? It looks good to me. May not have been initialized. Oh yeah, it's final. Final means you can only write to it once. Once it's been given a value, it can never be changed. But we'd better give it a value when it's created by the constructor, because otherwise you'll create this thing, and when you try and assign a value to it later on, you won't be able to. Notice I did this in the test code. It's crappy code, I know, but hopefully it's clearer now. I created the objects, and then I just wrote to their field. I mean, I should use getters and setters and all that sort of stuff, shouldn't I? It should have been an alert straight away I was doing something bad. Mind you, it would have been just as bad if I'd given them a setter. Here, I can't do this. Once A is created, it's now final. You can't change it. So what I'm going to have to do is initialize it in the constructor. So I'm going to have to give it a constructor now. Say public phone in number. Then we're going to say this number equals number. And that's it. Now it's a public field. I don't care. No one can change it. I mean, I probably still should have getters and setters because I've broken the uniform access principle, haven't I? Now it's compelled to always be a field. It can never be calculated on the fly. That's not good. But that's not the point of this particular exercise, so let's just leave it like it is now. Should compile. And what's our grumbling happening here? Well, now we're not matching our constructors, and if I fixed all that up and stuck numbers in here, we'd get grumbles because I'm trying to change a field that's final. Oh, in fact, to demonstrate that, let me do exactly that. 1,000 and 1,237, oh, 1,338, it's fine, and 141 and 29. And now we've got all these complaints down here. Hey man, what you doing? You're writing to a final field. Well, it doesn't speak it in hippie speak. It'd be nice if we could skin it to have hippie error messages, wouldn't it? So let's just delete all that. That's not needed now. In fact, because they're now data objects, we can just stick them directly in here. We'll treat them each instance of it as though it's just a single piece of data. So we'll create it gleefully whenever we need them and use them just as though they were ints or whatever. Even, or pretend they're not even objects, they're just primitive types. Oh, I'm missing the word new. That wasn't very good, was it? Okay, zap them. How is that going to work now? Let's have a look. Compilation problem. Oh yeah, okay. Well, now we're finding you cannot use, cannot update this thing, which is reference semantics, because it's a data object. It's immutable. You can't change it. So what I need to say is smallest so far equals all dot next, and down here I say smallest so far equals current. Just update the reference. So smallest so far points to the current one. There we are. See how does that work? And now they both work. Yay! And we've done it using value semantics. Is everything okay? No, it's not, because look at this. What if every time someone rings up, I'm a pizza parlor or something, every time someone rings up, I add their number to the known list of numbers that I get. But if someone rings twice and I add it to the set, what should happen? Well, you tell me, think about it. You add the same thing to the set twice. What are you expecting? I'm expecting the size of the set after these operations here will still be of size 4. But actually, what are we going to see? It's of size 5. Yeah, what happened? Well, Java, when it added this to the set to check if it was unique or not, it compared memory references, compared the references directly, and this failed. I guess what I'm trying to say is notice this is not the case. That is not the case, even though we'd like it to be. It's not. DDD. In fact, you can't even say dot equals. Okay. You're actually being too clever. Right? Can't even say new phone 123 equals new phone 123 because they don't. Because this is one memory reference that stores one object, and this is another memory reference that stores another object, and although the objects they're storing have the same field, the number, the int they're storing is 123, so you'd like 123 to be equal to 123. Objects containing 123 are not equal to objects containing 123. But we want them to be because this is data semantics we're using. So if we really want to have a data object, if we want phone to be a data object, then there's one more thing we need to do. We need to make sure that different objects containing the same value are regarded as being equals. And to do that, we're going to override the equals function. Remember, every object has an equals function. So let's override it. Well, what is the equals function? We'd better find the type of it. That's got to be easy to find because let's just pick a random class. It's got to inherit from object, so I can get straight to object that way, can I? Object has the equals method. Okay. That's the type signature for it. Let's see if it's got anything interesting to say for itself. Yeah, a whole lot of stuff about how equals is expected to behave. It's supposed to be an equivalence relation, isn't it? So it's supposed to be reflexive, transitive, symmetric, so on, so on, so on. You can read all that yourself. So make sure when you write your own one that it is that it does behave like equals should be. In particular, that if A equals B, we're expecting B to equal A, and if A equals B and B equals C, we're expecting A to equal C, and all that sort of stuff. Otherwise, Java might get terribly confused in places where it assumes it's an equivalence relation and it's not. So let's go. What is it? Public boolean equals obj. Okay, we're going to implement it ourselves. Now, I'm hoping that this is going to override the object equals method. Java has an annotation I can use. Just checking I was actually capturing. I suddenly went mad there thinking this wasn't being recorded. That would be very, very sad. Java has an annotation we can use called over. Stop that. Overrides. Is it? What's happening here? Overrides. Override. Thank you very much. If I put this annotation at the top of the method, that's telling the compiler that I'm expecting the following method to override a parent's or someone in the superclasses method of the same name. The good thing about this is if I get it wrong, and this doesn't override the parent one, the compiler will notice it and kick up a problem. And this is particularly important to do when you're writing an equals function, because it's very easy to get the equals function wrong. And if you give it the wrong type signature, what you're doing, remember Java allows you to have multiple functions with the same name and different type signatures, so it's not going to override the parent if you get the type signature wrong. It's going to create a new function of that different type signature, and then depending on how the function is called, you're going to call one or the other and get terribly confused and never quite know what's going on. In particular, you'd expect equals to not take an object here, wouldn't you? You'd expect it to compare a phone. That's what you'd expect. But if I try that, let's just return true. Everything's equal. Now let's think, if we say everything's equal, is that an equivalence relation? It is. Yeah, that's pretty cool. That's the world's best equals function. If I try compiling this now, I'm going to get a grumble. Equals phone, blah, blah, blah. It's grumbling because I'm not overriding. I've said I'm going to override and I'm not overriding. Yeah. So if I said object, presumably it's going to be happy now. Yeah, all numbers are equal. Okay, now I compiled it to demonstrate that all numbers were equal, that I got the type signature right and it was going to override. But notice, if you look down here, you'll see, we just got the output printed out as well. You'll see it's not working. The set is still not regarding them as being equal. What's going on there? Well, there's a problem with our equals that I'll get to in a sec, but let's just notice that there is a problem. I haven't implemented the equals function properly yet. Let me implement it properly. Actually, let's not. Let me tell you what the problem is, since it's arisen. The problem is that, what sort of set is it? Do you remember? My set in test phone. It's not any old set, is it? It's a hash set. It's a hash table. And you can imagine if I was implementing a set as a hash table, and I needed to have a function, I needed to have my add function work in the following way, that when someone added something that was already in there, I didn't bother making any change. How I would do it is, if the set was a hash table, is I wouldn't bother searching the hash table for the guy being inserted. What I'd do is, when someone gives me something to insert, I'd go to the spot where I'm supposed to insert it, in that part of the table, and if there's already some data in that particular cell of the hash table, I would compare my object with that data, and if they were the same, I wouldn't bother adding, and if they were different, I would. So in other words, I wouldn't use the equals method until I was actually in that cell of the hash table. So if the guys are going to different cells of the hash table, this is what I'm leading up to saying. If you've got two phone numbers, but they're being sent to different cells of the hash table, then they're never going to be compared with two equals, because my method would just say, oh, you're putting in an empty cell. Well, that can't already be in the hash table because it's an empty cell, so there can't be another instance of it here already. So the problem we've got here is that, I'm not explaining it very well, but bear with me, think about it. There's a relationship between the equals method and the hash method. In particular, we expect that if two things are equal, they should have the same hash value. That makes complete sense, doesn't it? Of course, if two things have the same hash, they don't have to have the same. They don't have to be equal. We know that about hash tables, but certainly it has to go the other way. So if you've implemented a hash function which gives different hashes to objects that we regard as being equal, it's not a very good hash function, is it? So now we've changed our notion of equals, we've also got to change our notion of hash function, so it's a legitimate hash function. So let's go back to phone here, and we better override the hash function. Override. I can't remember what the hash function is called. It's called hash value or something, isn't it? Let's go back. Hash code. All right, public int hash code. And if you go to the doco, which you should, and read all this, it'll talk about equals and the relationship between equals and hash codes and all that sort of stuff. It's not magic. When you think about it, it makes sense. Okay. So we're going to have to return a hash code. We're going to have to create a new hash code, and the hash code is going to have to be equal when the objects are equal. Well, here's a crazy hash code. Why don't we just return... What are we going to return? Can you guess what I'm going to say? We're going to have a hash value to represent our object. We want our objects to be the same when the number they're storing is the same. So we want our hash value to really only depend on this number here, nothing else, certainly not the memory location the things are stored at. Well, this number is an int, and the hash has to be an int, so why not just let's return that number and say that's the hash value, and we'll let a number hash to itself. Yeah, that's pretty cool. Awesome. Now let's see if that works. Unresolved compilation problem. Override cannot be resolved to a type. Oh yeah, thank you. Annotation. Start with capital O. Okay. All right, yay! So now we've said the number, two things with the same number. Oh, I haven't been that good, have I? We're saying everything hashes to its own number. So if two things have the same number, and they're, of course, by our new definition, they're going to be equal, their hash codes will also be equal, and everything's going to be cool. So this hash code now is a perfect hash code to use for equals as we want to implement it, but notice we haven't implemented equals as we wanted to implement it. We've just said everything is equal to everything. But that's still good enough, because the only things that ended up in the same cell here were the two 99s, or whatever they were, 2314 ones, so they were correctly detected as being the same by their two equals. But this would be bad code to issue now. You can see that, can't you? Because if you had two phone numbers that happened to have the same hash code, well, let's think, hash codes are ints and numbers are ints, so they're not going to have, oh, well, by miraculous coincidence, then this is going to be okay, because we're never going to have two different objects, two different phone numbers hashing to the same value because of the particular hash code we picked. But suppose our hash code was something else like this. Say, oops, number divided by 2, number div 2. Now it still makes sense. Things with the same number are going to hash to the same thing, but now we're going to get some collisions, aren't we? For example, 3, the number 3 div 2 is 1, and 2 div 2 is 1. So 3 and 2 will have the same hash code, which is fine, and our equals function will regard them as being the same, won't it? Equal. So if I just did something dumb like this, 3, 1, 4, oh, there we are. So I'm now expecting to get 5 numbers. What's going to happen when I compile? I'll get just the 4. Yeah, the second number here had the same hash code, ended up in the same cell as that one, and because of our stupid definition of equals, they were regarded as being equals, and it wasn't added to the table. So let's fix that, put it back to our old one, but let's write a proper equals method here, and there's a standard way of doing it. In fact, Eclipse will add it for me, but let me write it for you. If I can, I'll probably get it wrong. It's always worth looking this up in a book when you do it, because you've got to get it exactly right. If the object is equal to null, then they're not equal. If object is equal to null, then equal false, else, because a null is not equal to any object. Otherwise, if they have the same reference, if they're stored in the same location, then they better jolly well be the same. Otherwise, if it's equal to this, then they're certainly equal. equal. Okay. Else. Okay, so suppose then the other object's not null, but they're not pointing to the same object. Well, if they're not of the same class, then they're not going to be equal. So if object dot get class is not equal to this dot get class, then equal. See what I mean? You should always look this up. You're bound to get something wrong. Now the reason I have to check they're the same class is, remember, for the overriding reason we talked about before, the thing I'm comparing with has to come in as an object, even though I'm assuming I'm comparing a phone number with this. So I've got an object. I haven't got a phone yet. I've only got an object. So I'm going to cast it to be phone. I better not cast it to be phone if it's not really a phone being passed in. So first of all, I knock out the case where the thing being passed in isn't actually a phone. If it is a phone, woohoo, we're in. But if it's not, we'll return false. So if it is a phone, though, now everything's equal. Else, phone, phone, what am I going to call this object once I've cast it to a phone? Phone, I'm going to cast it and assign it to a temporary variable in case I need to do several steps. Well, I don't have to do several steps with it, but normally I can just do it in one fell line, so I can actually do a cast in line, but I'm going to actually create a local variable. That's okay. Phone other equals phone object. And now I've finally got another phone that I can compare with, and I'll say equal simply means this dot number is equal to, and now it's a primitive type, it's an int, right? So this is going to do a value comparison, not a reference comparison, equals other dot number. Whew, that is a lot of work. But now we've got our own equals. We've implemented a reasonable hash code which will collide when equals is true, and we've made it final, so it's immutable. We've had to initialize it in the constructor, that means, and now we've finally made a data phone object, and everything should work. Let's have a look. Here we go. Run the code, please. Can't I see the output? I shrunk it too small. Here we go. I've got 1, 2, 3, 4, 5 objects there. Oh yeah, because I changed that to be 3140. If I now run it like that, we're back to 4 objects, and everything is good and sweet. And that is the end of talking about value objects, data objects. And in a second, we're about to talk about reference objects.